Okay, so we're going to start with the sort of the history of solar cells. So what we're going to talk about today is really the fundamentals. When were they discovered? What is sort of the history, the seminal steps towards where solar cells are today. We're going to talk about the basics of what happens when like light hits a solar panel or a solar cell at the atomistic level. What is that light matter interaction like? What do you need in that material to be able to absorb sunlight and then generate electricity? And then maybe towards the end, what are some of the newer types of materials that are coming out in terms of solar cell materials? Doc, that's amazing. Thank you. I think isn't there Dr. WD4, is there an actual command? No, it's a positive command. Isn't there like a quote about him though? No, that one's okay, that one's funny. That's about horizon side. No. Apparently there is no quote 8. I hate you. There, that one's good enough. Yeah, that's good enough. Okay, so we're concentrating on real science today. Physics and chemistry and even engineering. I mean, it's not really a science, but definitely very little, no biology in today's stream. That's not true. Okay, let's start in the beginning. Okay, this is a protein. That's what all proteins like. These proteins can, assemble with other things and make cells, which make humans. And then humans actually did something useful and created solar cells. In the beginning, one human in particular, okay, created the first solar cell, right? And that first scientist or human to create a solar cell was Becquerel. Now, you may have heard of Becquerel. I think this is the same Becquerel, Henri Becquerel, who won the Nobel Prize along with Pierre and Marie Curie for discovering radioactivity. So Becquerel was kind of a badass. All right. Sure, Tanny, we are. Stank, welcome back. Yeah, that's fine, Stank. Applied science is fine. Okay, so this guy won the Nobel Prize, but he also basically invented the first photovoltaic. And by photovoltaic, I just mean light photo coming in and creating a voltage in a material, electricity. Basically shine light on something and get electricity out, or a voltage difference. That's what we're talking about. So Becquerel's paper on this was called Recherche sur les effets de la radiation chimique de la lumière solaire au moyen de courant électrique. Okay? Which is French for, y'all stand back, I'm going to shine some light on this stuff, and let's see what happens. Okay? It's French for research on the effects of chemical radiation of the sun, creating electrical currents. Right? Basically, he found this material that when you shine light on it, you registered an electrical voltage difference. Okay? That was in 1839. Okay? Not much happened for like 40 years. All right? People got distracted with like the Industrial Revolution or like the Civil War, or maybe even some like biology, low-hanging fruit science. But it wasn't really till Fritz in 1883 who was like, all right, Bex, I see your design and I raise you. Okay? I raise you because what's this? I raise you because I'm going to be the first person to create a sandwich where this sandwich part is a metal, okay? And this part Oh boy, I need a third part. There we go. Here's the sandwich. This is gold. And in this gold, other metal like brass, I think it was. I think this was actually brass. If I'm not mistaken, I don't really remember. Some kind of metal. All right, so there's brass, right? And then the sandwich stuff in the middle here, right? The PB and J, if you will, was selenium. Okay, and selenium is like right below sulfur on the periodic table. Okay, now okay, cool. Bria, welcome in. All right, so this was Fritz, and this was his contribution. He was like, okay, I can create this same kind of thing that Bex did back 50 years ago, but mine is much more efficient. And this is sort of the first time we have this sandwich architecture that really became the solar cells that we have today. At least, you know, the engineering of it, this sandwich architecture. Before, Becquerel had like these plates of stuff next to each other. He had like a piece of metal here and a piece of metal here, and he was like connecting a wire between it. And he was like, when I shine light on these metals, electricity seems to flow. Weird. And that was like it. And then Fritz studied it a little bit more and found the sandwich architecture was better. Yeah, that was the first really sandwich architecture we had. Now, there was really a leap forward 70 years later. Okay, now we have Bell Labs. And I don't remember the exact scientist who did this, but Bell Labs in like the 1950s made the first silicon solar cell. And this is still like, you know, the main man in solar cells. Okay, this is what you think of. When I say solar cell, you say silicon, solar cell. Anyways, this is what you think of. Now, there's many more new materials that we'll touch on probably later, but silicon got like the first early movers advantage. I think, you know, if you look at something like this, all of these very, I guess not all of them, but the leader in the clubhouse, the blue here is crystalline silicon cells. In the very early days, right, most of what was being worked on and had the best efficiency was silicon. And even, you know, as we go up today, that's still mainly the leader in the clubhouse compared to a bunch of other technologies, except for these sort of multi-junction gallium arsenides and some other things we might touch on later. Anywho, okay, silicon solar cells, the first one in 1954. And this is really where we're going to concentrate most of the lecture today and discussion. Sure, Q. Sure. Okay, so what is a silicon solar cell? How does a silicon solar cell operate, right? So let's talk a little bit about how this works. A silicon wafer looks like this. Here's a silicon atom, all right? It's bonded to another silicon atom. That happens to be bonded to another silicon atom. Okay? Yes, C. And silicon is right below carbon. You all know, okay, because you're good little chemists, and I've trained you, that carbon makes 4 bonds. Silicon, being right below carbon in the periodic table, also makes 4 bonds. Okay, and so we're not looking at the edge ones so much that are out here, although they can still make 4 bonds, right? But, you know, the ones on the inside of this is a crystal lattice of silicon, a bunch of atoms of silicon ranged nice and neat. So if these were all silicon, it's this really periodic crystalline structure. So this is a silicon crystal. Okay, and this silicon crystal is known as a semiconductor. Let me make sure I can actually keep this on the screen. Boom, nailed it. Okay, now what is a semiconductor? Okay, diamond is a lattice of crystalline carbon, for example, right? Here we just have crystalline silicon. Okay. Homonyms, welcome in. Sit down and pull up a stool and learn something, all right? We're talking about solar cells today. So here's silicon crystal. It's a semiconductor. Now, what does semiconductor means? It means like sort of conducting, right? You have metals like, sodium and what's another metal? There's like 80 of them on the periodic table. Any metal, titanium, sure, that's one. Nickel, copper, these are conductors. Metals, for the most part, are conducting. Non-metals, for the most part, are non-conducting, right? Things like fluorine and bromine, right? And oxygen, these are non-conductors. But you have some elements between metals and non-metals, often called semi-metals, things like silicon, for example, that are sort of conducting. And what that means is at absolute zero, they do not conduct electricity. But if you give it a little bit of energy, it starts to conduct electricity. And so you need to have a material like this so that when sunlight is acted upon it, it can promote this conductivity, okay? If you're always conducting, right, then the electrons are always flowing. What you really want in a photovoltaic or a solar cell is when sunlight comes in to initiate electricity, okay? So you have a semiconductor, all right? Now, the problem is this does not really allow for a controllable flow of electrons. Exactly, homonyms. Exactly. You can make it a specific temperature for it to conduct. You can shine the certain amount of light on it for it to conduct. And we'll talk about band gaps a little bit later. But you can make it conduct more easily by actually changing some of its characters. So what if we imagine, okay, in a world, imagine this silicon atom right here, see? We take out of there, okay? I'm just going to go over there and grab it and take it out. Okay, great, we did it. That was seamless. The animation was perfect. And I'm going to replace it with, oh, I could throw it, yeah. And I'm gonna replace it with a phosphorus atom. Here you go. Boom, nailed it. So here's this phosphorus atom. I'll just rewrite it. The animation works perfectly though. And I'm gonna place this phosphorus atom there. Now, if you look at the periodic table, which I have memorized and can draw perfectly, here it is. Boom. Okay, silicon is right here's carbon and here's silicon, okay? Silicon, you are here. Okay, great. So there's silicon. Now, silicon has 4 valence electrons, just like carbon. It wants to make 4 bonds, okay? But there's an element just to the right of silicon known as phosphorus that has 5 valence electrons. What that means is it has an extra electron. So while silicon usually has 4 electrons around it, phosphorus has 1, 2, 3, 4, but then it's got an extra one, all right? It's got one just hanging out here. And now this is the ticket. This is the ticket to ride here, okay? This extra electron is not bound to any atom, and it's sort of free to diffuse around. Well, we haven't gotten to the sunlight yet, William, but most of the silicon crystals that you're talking about in solar cells are of this type, okay? What we've done here is we've doped the silicon with phosphorus, okay? And this doping you do sparingly. So about 1 in 10,000 atoms is doped. Okay? It's super dope. Exactly, boing, Professor Servant. We'll get to it later, William. Always dope sparing, that's right. You got to stay below the detection limit when you're doping, okay? Now, we've doped this with phosphorus. This in particular is known as an N-type semiconductor. Okay, and the N here stands for, who wants to guess? Chat, 100 bonus points, okay? 100 bonus points on the line for who can tell me what the N, even take a wild guess here, what the N stands for in N-doped.
Bad news, everyone.
No, positive is wrong, boring Professor. Jared, exactly right. All right. All right, I will spam and delete all the other joke answers from the chat. N stands for negative. Poggers.
Good news, everyone.
Yo, Jared, thank you very much for the follow. Appreciate it. This N stands for negative, right? And why is it negative? Because we've added an electron. Wait, you've added something. But what we've added is an electron, which is negatively charged. We have added some negative character. So we're adding extra electrons, creating this N-type semiconductor. So this is a negative type semiconductor. You can also dope with other things. You can dope with something to the left of silicon on the periodic table, which is missing electrons. You know what we would call that? P-type semiconductor. So you can dope with something to remove charge, right? And that's called P-type semiconductor. The P obviously standing for pterodactyl. Which begins with a P. Duh. All right, so you have this N-type semiconductor, right? And the key here is that you've added diffuse electrons. You've added some extra electrons that can move around. That's going to be key. Spoiler alert, it's going to be important. Jared's just the TA. Mean Machine, welcome on back. Pebble Nut, welcome. Why not? Look, I didn't invent this, okay? So this diffuse electron is going to be important, all right? So we've created this doped silicon, right? And now we're going to zoom out a little bit, and we're going to make a whole layer of this N-type, okay? And in this N-type layer, right? This is N-type silicon, right? Meaning 1 in 10,000 atoms is not silicon, but it is phosphorus, okay? So this is the N-type silicon. So you have some silicon here, and here, and here, and here, and then every once in a while there's a phosphorus, okay? What does that mean? It means you have all these nuclei, which are positive, yeah? And you have electrons that go with those nuclei. And I'm simplifying, there's really, 4 valence electrons around a bunch of protons in each silicon atom, but for, demonstration purposes, this is equal amounts of electrons, the pink spheres, and protons, the positives. Those are all the silicons. But then every once in a while, right, you have this nucleus that is phosphorus with an extra electron. And it's this extra electron okay, maybe there's another extra electron here. Right, so we have an extra electron right here because it's a phosphorus atom that's doped, and an extra electron here because there's another phosphorus atom that's been doped. This is less than 1 in 10,000, if you were wondering, but for demonstration purposes, there it is. Now, underneath this layer, I'm going to put regular silicon. Just regular old boring silicon. Okay? So there's a silicon and 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 a silicon, 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 silicon. Okay? Now, each of these silicons has an electron, sure. Boom, 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 boom. But there are more electrons up here. It doesn't get more complicated. Well, it does, but it's not too much more complicated than this. What you've done here, okay, is created more electrons up here. And down here, you have less electrons. These electrons that you've added on top of this are diffuse, meaning they're not really tethered to the protons. In a typical silicon lattice like this, right, where it's all silicons, like shown here, these electrons that are symbolized with lines, where each line is 2 electrons in a chemical bond, these are very stationary. They're tightly tied there to the positive silicon cores, right? But this extra electron with the dopant phosphorus is much more diffuse. It can move around throughout the material. Okay, so if you have more electrons up here and they're diffuse, you're going to wind up with a general migration of some of these electrons down. So this electron here is going to be walking around, and it might find its way down here. Why? Because there's less electrons down there, and by comparison, more positive charge. So it sort of migrates down there. And this other electron from this phosphorus dopant might also diffuse around and find its way down there too. And so what you have now, just by layering N-type silicon on top of regular silicon, is you've created this electron sort of migration, and you've set up what will be boy, that's a terrible, I don't even like that color. Let's try this. This is an electric field, okay? You basically have created this imbalance in electrons. Okay? So there's sort of this electrical potential that drives some of the electrons down. William says, doesn't that make the silicon angry? So these are sort of diffuse electrons, right? There's still positive cores down here, right? So there is still like this attraction, and there happens to be space for the electrons in those silicon atoms to, accommodate and not be too bothered by the new electrons that are being introduced. So, the electrons that are bound to the silicon are kind of, think of it as very close to the nucleus, which is only kind of true, but that's how I like to think about it. Whereas these diffuse electrons are much further out and can kind of migrate around and see all the positive charges and be attracted to them. Okay, so, in a way, it perhaps makes them not as happy as they were, William, but it doesn't displease them too much. Okay, because these electrons aren't tied to a singular silicon atom, it is sort of shared amongst all of them. Okay, so this is what we've set up now, an electric field. Get it? Got it? Good. Okay, so this electric field is really only, exactly, Professor EXP, these are swinger electrons. This electric field is really, I haven't drawn it great, but let me draw another version of this. Okay, so let me draw this again. You have the N-type silicon here. Okay, and you have the regular silicon down here. And what I should have done a better job, showing before is that really it's only the dopant atoms near the silicon whose electrons wander into there. Okay, and let me make this actually a bit thicker. Okay, so here's thick. Okay, we need, chat, we need a very thick layer of N-type silicon on top of a regular silicon. Okay, and remember, these are crystals. There's a bunch of silicons here. It's really only the phosphorus is down here near the pure silicon, whose electrons are close enough to diffuse down into this layer and create this electric field. So really, the electric field probably only exists, right, in like this region. Okay, so there's my electric field. Okay, now why is this important? This is important because now we have to introduce, okay, the real star of the show. Okay, everybody? Everybody put your hands together, give it up for the sun! The sun! People claps in the chat, thank you. Okay, now, preemptive boo. No, I would never joke about the sun. Okay, it's a little too hot for me. All right, so here's our electric field that's created. Now, the sun, is always emitting light. It's what suns do. Okay, unless of course, it's nighttime and the sun's been turned off for a few hours. Right. But outside of that, it's always emitting light. Okay. The star of the show is the sun. Yeah, thanks. At least somebody caught it. It was subtle, but it was there. All right. So this sunlight, okay, is coming down here. And maybe it interacts with a silicon atom up here. Remember, these silicon atoms are in lockstep and arms with other silicon atoms. And maybe this sunlight finds this silicon atom right here. What sunlight can do, remember I said these electrons here in the bonds of silicon are very stable and they're stuck there, okay? But sunlight can provide the energy to remove that electron from the atomic silicon. So sunlight can create an electron. Now it's not creating that electron out of thin air, it's leaving behind an extra positive charge on the silicon. Essentially, it's breaking a silicon-silicon bond and removing one electron. And that electron is sort of able to now migrate around and diffuse around, kind of like the extra electron in phosphorus, right? So this is what the energy of sunlight can do. It can come in here and break this bond and create this free electron that can go and migrate around. Now, if it is up here, outside of the electric field area, there is nothing pushing on it. An electric field will push a charge because that charge responds to the field and moves. Okay, this electron is not in an electric field. That electric field is only down here. Okay, so it migrates around for a little bit and finds the positive charge again. Okay, and annihilates this hole. Okay, so basically you have an electron here and you have a hole which you've left behind. Okay, really what I'll say here is sunlight creates an electron hole pair. Okay, now if that is up near the surface, not where the electric field is, then that electron and hole just annihilate each other, and it's like nothing happened. Energy in, they recombine, energy out, dissipated as heat, you're fine. But if this sunlight happens to encounter a silicon atom down here in the electric field area, sunlight's going to do what sunlight's going to do and go sha-na-na-na-na-na-na-na. And it's going to break, and it's going to pop this electron off. Now this electron is not just going to go all nimbly-wimbly around. No, because it exists in this force field, this electric field, that is going to be pushing the electron. And it pushes it down. okay? And the silicon positive charge that's left behind is pushed up. And now it's this function, this very act of light creating this electron-hole pair within an existing electric field that separates the electron-hole pair that gives us electricity. Okay? Because what we've done here is we've created an electron and created a hole or a positive ion. This hole here is really just, what the electron left behind. People call them holes, right? Like, oh, you're an A-hole or you're an electron hole. But really what they mean is the ion that you've left behind that is missing a negative charge. So this hole is just a missing a negative charge, but it's really a positive charge net, okay? So now you have this negative charge moving south and this positive charge moving north, okay? And it's this now separation and flow of charge that is important, okay? So electron hole pair created in electric field results in a net movement of charge. Okay? Any questions there? Does everybody understand that, right? So again, we've layered this doped silicon on top of regular silicon. There's a sort of natural diffuseness of these electrons from phosphorus that make their way down into the regular silicon that sets up this electric field. Now we expose these things to sunlight, okay? And the sunlight comes in and creates another electron by breaking a bond in this electric field region. And since there's a field there, there's a force pushing on this newly created negative charge. This new charge that you've created now gets moved, okay? And this net movement of charge, okay, all the foreheads in the chat, you call this electricity. That's what you would refer to this as, okay? And so we're creating electricity out of sunlight in this solar cell. That's what a photovoltaic does. Photo light, voltaic for creating a voltage difference or electricity. The worst says, why would the electron move to the silicon layer? So back up here, why is there this net diffuseness? So two reasons, okay? One is there is more electrons up here than there is down here. So there's more electrons here, more negative, less negative. So the things are going to move from higher negative to lower negative, okay? Because they're repelled by other negatives, right? That's one way to think about it. The other way to think about it is just the ones that are near the border will naturally spend a lot of their time down here and create this electric field. So if they diffuse up, there's no real net difference. But if they diffuse down into this different layer, now you're creating this net difference in this electric field. Good question. Hey, EXP, thank you so much for hanging out. Appreciate it. GZB, welcome back. Why do electrons go out? So we haven't gotten to that, Jared, but you can have another p-type layer under this. This is sort of our first introduction here into the very simplest type of solar cell, which is really silicon doped and on top of other silicon. Now, William, one of the answers to your question, okay, is that it gets pushed down because of this net difference, this electric field. A field exerts a force on a charge, right? You have a magnetic field or you can have an electric field, and really that's the same EM field, but you can have a gravitational field, and that does something on gravitons, different lecture. What you have here is an electric field that exerts a force. So the electron normally is bound, and even if the electric field is present, right, that's a pretty small force relative to the chemical bond that is keeping the electron in place between the silicon atoms, okay? So this is strong right here. And even if that chemical bond is down here in the electric field, nothing is happening to that chemical bond because it's so strong. Now, if I break that bond with sunlight and liberate this electron, it's not localized to be in a chemical bond anymore. and it's very diffuse. It's under the whims of any exertion upon it in this electric field that it is now like, oh my God, I'm in an electric field. That electric field exerts a force. And in this, the way I drew it in the picture, it's down, okay? But it could be up. It could be just depending on how you sandwich the layers. But in here, it's going to push positive things up and negative things down, okay? And so that's why I've drawn the negative sign going down. Okay, you could orient it the other way. The big point here is that you have this movement of charge, which is what we're after. That's what's called electricity. Now, yes, chemical bonds are OP. Please nerf, scientists. Yeah, the electrons hate each other enough that it pushes them down. Yeah, I think it's fine to think of it that way. Yeah, I think that's probably okay to think of it that way. As a sort of a difference in density of total charge, and the more negative charge you have in one area will force new electrons out of that area. Okay, so now we have a movement of charge. We're not done yet though, right? Because now we have to do something with this charge. But we have sunlight that's created a electron-hole pair that results in the net movement of this charge, which we call electricity. But it's not really electricity yet, okay? Because the other thing we need here here's our N-type, here's our silicon, here's our sun. Now, my dad used to say, oh boy, look at that sun, sure is bright. He was talking about me, because he was my father. Where's homonyms at? It's a homonym joke. Okay, so that sun sure is bright. This sun, it creates electrons and holes. The electrons flow down and are now here. The positive holes left behind are here. But now what we're going to do is we're going to, stellar joke. Thank you. I appreciate that. We're going to attach a very, very impressive thing. This thank the engineers for this very, very impressive leap of intellectual genius they had. Well, how about we hook up a wire? Okay, and so we take and we put a wire on here, a piece of metal, and we run this metal all the way around to the other side and hook it up where? Oh, let's hook it up to the other side, boss. Okay, and they hook it up here. And instead of being a continuous piece, they're actually like, well, wait. Let's put a light bulb in the way, okay? And they put a light bulb right here. And now that light bulb shines light because you're pushing electrons. You have a ton of them down here, and electrons have no problem traveling along a wire, especially when they're like, oh my God, there's positive charge all up there. Okay? Of course, there's an electric field here that's keeping us suppressed. It would be great. It would be great if the electrons could just be like, oh man, I'm just going to go right back up here and annihilate. Well, you can't. There's an electric field. But if you look over here, these brilliant engineers have hooked up a wire, and now as an electron, you can be like, yeah, whee! And you go through this resistor, and that resistor thermally heats up and emits light at a certain threshold of energy, and some light's given off, and the humans are like, yay! We got light. Okay, and the electrons eventually go back over here and annihilate the holes. Okay, so now this is electricity and electrical work that you're getting out of this thing based on a totally passive material. This thing's just sitting there in the sun trying to like enjoy its life, and the sunlight comes in here and causes all this chaos to happen, right? There's no moving parts. It's brilliant. Okay, we don't need an internal combustion engine. We don't need giant turbines, not giant turbines. It's a different lecture. Giant turbines swinging and killing all the government drones, i.e. birds. All we need is this passive material sitting there, subjected to sunlight. And if we have that, then we can create a movement of electrons, and we can use that movement of electrons to do work, either directly right next to the solar cell, or we can perhaps harness it and put it in a battery for storage to be used later in our giant laser. Okay. As of now, no moving parts, PebbleNut. The light doesn't create it doesn't create the electrons out of thin air. It is basically removing them. It's a great question, but think about a general picture of an atom. General atom. Here's your proton core. Here's your electron around it. Right? So basically all the sunlight is doing is saying, electrons are pink, the electron negative is attracted to this positive, right? And so there is like this energy that's keeping them together. Think about them as two magnets, William. What the light does is come in here and break apart those two magnets, okay? So all the sunlight is doing is coming in here and giving this electron enough kinetic energy to leave. And so it's no longer tethered to that atom. That's how you want to think about this. It's not creating an electron out of nothing, right? It is liberating an electron and making it mobile, allow it to diffuse around. And the moment it's released from its chain to that proton, to that silicon atom, it realizes, oh my God, I'm free to do what I want any old time. But then it's like, there's an electric field around. Oh, shoot. I thought I was free, but really there's this subtle push down on me. And so I'm going to be like, do-do-do-do-do-do-do, and I'm going to wander down here. I'm not paying any attention to my atom anymore, but I have to do something under this electric field. And so I move in response to it. So great question, William. Lowell, welcome on back. You're taking the energy from the sun, overcoming that chemical bond, and then using that electron to do electrical work. So you're not creating energy. Matter cannot be created nor destroyed. Energy cannot be created nor destroyed. But you are transitioning from solar energy, right? Breaking apart chemical energy, sort of, and creating a flow of electrons that can do electrical work for us. Yeah, PebbleNut. So there is a lot of discussion on electrical photovoltaic waste compared to, say, nuclear waste. Look, solar is king. It's clean. It's renewable. We continue to make improvements in efficiency, but there is, in the research of it, in the scaling up, in the manufacturing of it, there are oftentimes a lot of waste, more waste than is created typically in nuclear or ever in nuclear waste. So it is a problem, and we have to learn how to recycle these things. Negative plasma, welcome in, dude. Exactly, Nafron. Okay, so solar panels degrade because there's a broad band of spectrum of light, some of which is highly energetic, to do irreversible damage. Okay, remember, sunlight is putting out a broad spectrum of light. We'll talk about this in a moment. William, don't fully understand it. So, yeah, that's okay. The point is, you're not creating matter. You're just moving electrons really from being tethered to an atom. You're giving it a kick. So we often, I guess I drew it here as a wave, but you can think of sunlight as actually photons, which are little bullets. So think about this electron that's sitting here and is happy tied to its atom, but then you come in here and you shoot it with this sun gun, and you're like, psh, you're going to kick out this electron. And now this electron's just off living its own life. But it's living its own life when there's a bunch of other electrons above it. And now it's like, okay, I'm not so worried about the proton anymore. I'm worried about all these negative charges above me. So those are going to repel me. And now I've created a movement of electrons. Before it was tethered to this atom, but now it's moving. And it's that movement of electrons and a net migration of a lot of these electrons that I can get to a wire that I can connect to the other side of the positive away from these electrons. back to its initial silicon that it left, and it's going to recombine there. Okay. I don't know how fast the panels degrade. It depends on the type of material you're using. Better solar cell design says give 25 years to still be 85% efficient. Does the photon hit the electron directly? Yeah, so William, it's a great question. I'm going to tell you now a lie. And I'm just going to say, for the sake of this argument, the electron bullet, or the light bullet, the photon, hits the electron directly. Okay. Really? The best ones are 45 Faraday. Really what happens, William, is that this is not really a particle or a wave, but something that is described by both. And this electron isn't actually a particle. It's like this superposition of a wave with some particle-like details, and it's somehow the wave mechanics of each then interacting in this time-dependent manner that creates this sort of scattering, and it's quantum mechanics. Too much for here, okay? I think the best thing to do is imagine this as a sun bullet, i.e. a photon, being shot by the sun. And here's his arm. He's like, and a trigger goes this way. And he's like, pew, 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 solar bullet. And this electron out here is like, ah, and it gets kicked off. Okay. But it's really much, much more complicated than that. And we don't have a time for a full quantum mechanical treatment here. Okay. Allison, welcome. Yes. This Allison suggested the solar panel stream. You haven't missed much. Well, that's a lie. You've missed most of it. But we talked about the history. We talked about doping. We talked about sandwiching a doped silicon on top of regular silicon, which creates this net migration of electrons, creating an electric field. And then when sunlight comes in and detaches an electron from a silicon atom within this electric field layer, then the electron's free to leave the atom and migrate. And when that electron migrates, that's a net movement of charge that you guys in the chat would call electricity, and we can use it to do electrical work if we attach a wire. So that's where we are, okay? That's where we are. Now, yes, Larry, oftentimes when we talk about potential, whether it's electrical, gravitational, any potential, a lot of times the like water pipes, buckets leaking, these sorts of things are a good way to think about it. Yeah, so they retain 85% of what their efficiency was to begin with. Now, a single a sandwich structure like this, in theory, is only 33% efficient. So you can never get out more than 33%. So you need basically 3 photons in to get 1 electron out. That's one way to think about it, okay? So single sandwiches, like what we've been discussing thus far, has a theoretical limit of 33%. Well, God, this is the internet. 33.33, repeating, of course. Leroy Jenkins. Okay, so that's the theoretical limit. You can look it up. It has 2 guys' names attached to it. Basically, there's the solar spectrum, there's heat losses. You can never do better than 1 out of 3 with a single sandwich structure. Yeah, I agree. Patine, welcome on in. Plenty of photons. Statney, welcome back. not an official formal one. This is more interactive, Statney, so please interact. Okay. So now, this is the basics of a solar cell. Okay, and if you see a solar cell, it generally looks like this. And I guess actually I should say this is like a solar panel, and it's like and then it's like okay. And basically each one of these little guys is a single solar cell. Okay, so you make these little square or rectangular solar cells, and these individual units are the cells. Okay, in much the same way, oh man, I promised there would be no biology. Oh well, and in much the same way like the building blocks in your body are made up of cells, well, the building blocks of a solar panel is made up of cells. So if you put enough cells together, and remember, we need wires attached, so each one of these solar cells has a wire. These right here are the wires. These are the small wires. Okay. And these are the thick wires. Okay. Each of the small cells has to be attached with a small wire. These small wires then go over to the large wires that do all the most of the current carrying. Okay. So each one of these little solar cells is in here. They're attached in a row. Okay. And this row you might call like a solar module. Cells into modules. Okay. Modules become then panels. And panels become arrays. So that's some of the lingo and verbiage for these solar cells. So the solar cells are the small little silicon, sandwiches you make. Then you lay them out in series. You get about a 0.5 volt of each. And you can get then much bigger voltages by connecting the thin wires to these thick wires. And you're off and running. Larry says, I've had panels for about 15 years. Nice. They have lost output a bit. I still use them for charging small stuff. I would have to test them to prove the loss. Sweet. Love it, Yuri. I mean, look, biology is just applying chemistry to much larger systems for people that hate or are scared of math. What makes some solar panels more expensive than others? Well, first, the raw materials they're made from, whether those materials are rare, they can be more expensive to mine and isolate or create from electrolysis, or all the R&D that goes into developing the solar panel. Now, one thing I didn't mention here is most solar panels are like blue, right? That's why I drew it here in blue. Ideally, you want black, right? Because black is the best absorber, but it tends to be blue because you're covering these with an anti-reflective coating to help keep the sunlight striking the surface near the surface and prevent it from being scattered, and also to protect from like dust and stuff like that. So they tend to be blue based on like the anti-reflective coating. Okay. Yeah, and they actually have a roll-up array. So, these solar arrays you think of as like fixed panels that you've put together on like the International Space Station or even the Mars rover or something. But now we just watched a launch a couple weeks ago on my channel, and we saw they have this foldable one. So, these voltaics are not super flexible, but if you space them apart a little bit and you put them onto a fabric, then you can roll up the panel. And so they would like to unroll this solar array on the International Space Station. Dust and pollen kills my panel efficiency. Yeah, I mean, that dust is just reflecting and absorbing the light instead of your solar cells. Yes, there are some benefits, Evo. Yeah, Uncle Doc was in here earlier and said, Broken Pliers said they had trouble unfurling them. Basically, space origami, exactly. Okay, so that is the first part of the lecture. Okay, that was good. That was good. I like this. Okay, where we talked about the history and then some of the basics here. The second part of the lecture is probably going to be shorter. I want to talk a little bit about the solar spectrum, what light is being absorbed, and how we can increase the efficiency of these solar cells. Yeah, apparently, Patine. They tried to.
Good news, everyone!
Alex, thank you very much for the follow. Now, please get back to work developing solar panels, okay?
Get back to work, you slacker.
Freaking slacker here watching Twitch instead of doing science. Imagine. Okay. So, what now? What next? Next, I want to talk a little bit more about this light-matter interaction and this energy and efficiency. Okay, so what we're going to talk about now is power, voltage, current, band gaps, efficiencies, right? All these buzzwords that people love to say and don't really know what they mean. Okay, so here is a basic band gap diagram, right? So what we're talking about now is band gaps, okay? And we've already talked about this a bit. I just want to concentrate in presenting it a different way. But what you have here is a whole bunch of atoms, right, of silicon in a crystal lattice. Now, these electrons, these valence electrons of silicon, valence meaning the outermost electrons of silicon, are in these chemical bonds and they're sort of localized, okay? And the energy of these valence electrons, we're going to depict here with this valence band, okay? So that's what I'm calling this. Okay, there's no numbers on the energy scale because energy is a relative scale anyway and it doesn't matter. Okay, the point is this valence band lies below something called, we'll ask the audience here, what is this upper band called? What is the upper band called? Trying to see if anybody's actually paying attention. Conduction band! Hey! Exactly, this is the conduction band. So, before I sort of glossed over sunlight coming in and breaking the chemical bond or liberating the electron, that picture is not totally correct because there's electrons that sort of, in a solid, it's not just a single atom and an electron, but a bunch of atoms and a bunch of electrons. And so those bunch of electrons organize themselves in electron bands that have a certain energy. But the point remains that they aren't able to move and diffuse. Why? Because there is a gap to getting to a place known as the conduction band. And this is where the material becomes conductive. So a semiconductor has a small band gap. And you want this band gap to be present, but not too big. Because again, you want it to be able to conduct and move electrons on command, with you giving it enough energy by heating it up or by sunlight, okay? So what you want here is to provide this electron that's in this silicon atom, but really it's a bunch of electrons in an array of silicon atoms known as the crystal solid, okay? But you want to give this electron in this energy state enough energy to start to diffuse around. What happens if it gets this much energy? it falls back down. It doesn't have a place to exist in. Okay, so this is just a diagram, an energy diagram that's meant to show you how much energy do I have to give this electron to get it to break free from its silicon and wander around. Okay, it needs to be able to go into a state where it can wander around and be conductive. So that's what we're talking about here. So the sunlight that comes in, okay, has to have enough energy. I should say, has to have more energy than this band gap. Okay, and if it is, then the electron from the sunlight kicking it off of the silicon atom will be able to move around and diffuse, and we can use that then to do electrical work. Okay, if the sunlight doesn't have enough energy, then it can't move the electron into the conduction band. It can't break it free from its atomic core. Okay. Procyon, welcome back. Yubi, welcome. Does the sunlight also break off atoms? So atoms are much more massive and not really mobile. Although, there is a slight vibrating around of these at any thermal energy. So, I mean, hypothetically, the atom itself could be diffused, but, the atom is how much heavier is the atom? Is it like 100 million times heavier? So it's just much slower. Like the energy needs to be so much greater. So, the diffuseness of the electron is like crazy. And the electron's like, or the atom's like, okay, I guess I'll move, right? Super slow. So in theory, William, yes, it'd be possible for the sunlight to create a mobilization of an atom, but it's negligible compared to this mobilization of the electrons. Okay, so yes, so William, you could promote it into the conduction band, or you could, above that is something called like the vacuum level. It depends who you talk to, what they call it. But yes, if you give it enough energy, the electron can go way up and break free from all the silicons and go shooting off somewhere else. So yes, that is possible, but it only takes, the highest of energies to do that. Yep. And that might be in part of the degrading process. Okay, so this electron that's now put up here, right, can be conductive and can find itself a wire and can go do electrical work. Now, one of the things I want to mention here is that this band gap I've mentioned, okay, is basically the voltage difference. Okay, whereas the flow of electrons, based on the number of electrons you get up here, is the current. Okay, and the power we can get out of solar cells. Okay, this is big if true. The solar cell power is, get this, voltage times current. Now, Procyon, I knew they were passing it. I didn't know it'd be observed already. Dang. Let's stay on topic for now, all right, and keep it at least related to the lecture, guys. So now we want to think about how much energy can we get out of this, but really how much power, right? Can we light a light bulb with this, or can we actually power our TV? Okay. Well, the power is voltage times the current. And here is the rub. Here is the conundrum. Exactly, lol. Exactly. To get your voltage difference up, you want the band gap to be larger. More voltage, more power. But the higher the voltage is, the more energy you need to get the electrons to move. Electron movement is current. So the greater the voltage difference, usually the less the current. And so these two are somewhat, inversely related here, that when you get voltage to go up, you get current to go down. So it'd be great if you could turn up the voltage and current to increase the power, but you can't. No, BMP, that's actually wrong. No, you typed uppercase I. It's or you typed lowercase l. It's uppercase I, actually, BMP. So no, that's not going to get you any credit here. Okay, so your power is voltage times current. The solar spectrum is something we need to talk about. I know you guys have been like, Prof, when are we going to talk about the solar spectrum, Prof? Okay, so here's the solar spectrum. Okay, at least the one on Earth in red, all right? Now, the sun puts out a bunch of different light, okay? It's not all just yellow, okay? It's white, meaning it has a bunch of different colors, and even that color is only the visible spectrum, which is a really small amount of the whole spectrum, right? So all of this in yellow is what leaves the sun. Everything in red is what reaches the surface. So the red line here, the red graph, is really what we're concerned with because our solar cells normally are on Earth. Now, if the solar cells are in outer space, well, then we have the full solar spectrum at our, pleasure. But really, on the surface of Earth, it's just red. The point is, we would like to utilize all of this light, okay? So on the left, lower wavelength is the highest energy. On the right, highest wavelength is the lowest energy. So remember, this band gap is what the sunlight has to overcome to get the electrons to move to give us electricity. Okay, so when the sunlight comes in and breaks this bond, it's only breaking the bond, and really it's liberating an electron. Really, now we're getting more technical. It's not just breaking a bond, it's moving an electron from the valence band to the conduction band. It needs to have this much energy. What is this voltage difference? Something like 1 electron volt is the energy separation. So it needs about 1 volt. Maybe it's half a volt, okay? So that energy, I don't remember what that is on a wavelength, but that's not way over here on the right. It's somewhere, actually I might know. What is that, like 800 nanometers or something? No. I don't recall. 1064 is 1.5 EV or something. Anyways, so there's a compromise here between what is the band gap of the material and how much of the sunlight we can utilize. We want that gap to be small so that we can use all of the sunlight necessary, right? But if we make that gap too small, okay, then that hurts our power ratio because the voltage is lower. Thank you, Zoiku. Yeah, appreciate it. Type them in there. Annika, welcome. Okay, so you need to absorb, the main point here is you need to absorb lots of sunlight. And by that, I mean a large range of wavelengths. To produce a decent current. Right, so current I, okay? But you want to preserve a decent voltage. So this is the trade-off. Okay, because if you design a material with a very low band gap, such that all sunlight can be used to move from valence band to conduction band because it doesn't take very much energy to make that jump, great, you got a lot of current, but your voltage difference is very small. Okay, and the opposite is true if you make a material with too large a band gap, right? Then you're throwing away a large part of the solar spectrum because when the sunlight comes in, it doesn't have enough energy to reach all the way up there. It only makes it halfway, and it can't conduct. It falls back down. Okay, so this is the trade-off to get a good amount of solar cell power out. It's this voltage versus current argument. Okay, and it's this sort of trade-off with the addition of heat losses that again limits all of these solar cells to a theoretical limit of 33.33, repeating, of course, percent. Okay. Lambeezy, welcome back, dude. We're getting close, but you need like 100, I think, consistently. We're not there yet. Appreciate it, though, bud. How you doing? You taking summer classes? Well, no, I know technically you need 75, but you can't hit... basically, from what I hear, is you want every stream of your 12 to 15 streams that month to have greater than 75 and preferably much, much greater. So you're not really a shoo-in to partner, I think, until you have like 100 CCVs, like every day you stream. And then it's a good bet. So just because you can apply for partner doesn't mean you'll get partner. I hope so, Lambeezy. Good luck, dude. Okay, so this is the theoretical limit. Now, I hear all the cries. Oh, great, on the sidewalk. Way to derail the stream. Now everybody's going to be Googling murder hornets. %33 is the limit. 33%. So here's 33%. Wait, Prof. In 1990, we were doing... We were over 33%. I thought you said... Look at this, 47%? Enhance. 47%, 44, 39, 37, 36. And you may not know this in chat, but it does turn out that 47 is greater than 33. Okay? This is true. I think. What about this other solar panel at 43%? That's also greater than 33. What about the one at 37%? Also greater than 33. So Prof, tell me this, riddle me this, smart guy. How is it that there's a limit of 33.33%, repeating, of course, when all of these here have higher than that? Okay, Max, great question. But is it greater than 33.33? And yes, it is. It is. Exactly, Neptune. 1 times 1 does equal 3. Very good. You've been watching Boring Math Professor stream, I sense. Okay. How can this be? Here's how you do it. You guys are always asking me, Prof, how can I get rich? Well, stream on Twitch because this is just free money, right? This is the most lucrative business. But if you can't stream on Twitch, okay, design a solar cell that gets greater than 33.3% efficiency. And how do you get that? How do we get money? How do we get more efficient solar cells? Triple question mark. Okay, probably something quantum. That's a great question. Much higher. 90% probably, William? Here's how you do it. Okay, it's really not beyond you. Lambeezy, I like it. Greg, thank you very much for the alert. Use more wires. No. Oil wins again. Yeah, well, problem with that is, have you seen how hot it is out west? Lol, very good. More layers. More is better. Okay, here's what we're going to do. Okay, remember, this is taking place in a sandwich, right? And what's better? Okay, chat. Here you go. Boom. Boom. This is our sandwich. 2 pieces of bread. Mmm, delicious. I spoil you. Okay, this is our sandwich. What's better than a sandwich like this? 3 layers. 3 layers is better. What's better than 3 layers? 4 layers. Let's make a 4-layer sandwich. Okay, so what we're doing is adding layers. How does that help? It's all just 33.3%. Nay. What we're going to do here is make 1 layer with a band gap, okay, tailored for red light. We're going to make another layer with a band gap tailored for green light. And we're going to make a final layer tailored for blue light. Okay, and now our sun, boy, that sun sure is bright. Our sun up here, our sun is up here, right? Sending its light down, okay? It encounters the blue layer first, which is the largest layer, right? The red light is too low in energy. So the red light doesn't do anything in the blue layer because the blue layer has a band gap that is like
Good news, everyone.
this big. All right, that is thick. That is big. Okay, that is not being traversed. Thank you very much, Neptune, for the follow. Appreciate that. By the red light. So remember, the solar spectrum looks like exhibit A here. So the blue light, the high energy light down here, gets absorbed in the blue layer. The infrared, the red light, the higher energy light, and the green light in the middle just goes through. So effectively, you're getting all of that blue light absorbed, right? And you're not making any trade-off because the red light that's not good enough will go down to the red light layer. Okay? So in this way, by sandwiching material 1, 2, and 3, okay, you can put these stacked in series and get a much better total collection of energy, which is more efficient. So this is what gets us into the 40s. Okay, there's still a massive amount of wasted light and heat loss and these types of things. There's still a trade-off within each one of these layers. There's not perfect. If 3 is better, is 30 even better? Yes and no. There are interfacing issues where you lose energy as well. So there's a trade-off there. So this only gets us to like 40%, but that's still, not terrible. Okay. The photons are doing different things based on what color they are. So the blue photons have a lot of energy. So they're going to be used up in the layer where you need that much energy, or the blue light, to promote an electron into the conduction band. Okay? And the light is traveling down. Remember, this is sunlight. It's going to go through all of it, but the blue part of that sunlight is going to be absorbed here. The green part of the sunlight is going to be absorbed here, and the red part of the sunlight is going to go through the first two because it doesn't have enough energy to do anything in those layers, and is going to be absorbed in the third layer. Okay? Usually if it's a single layer, you're making a big trade-off and throwing away a lot of light to preserve some voltage difference. Here you don't have to do that as much. Yeah, guy doing guy thinks that's a good way to think about it. These are different semiconductor compounds in different layers. Yeah, so the band gap, right? A small band gap would be red, a medium band gap would be green, a large band gap would be blue, and you can tailor that based on the dopant you're using and based on the material you're using as well. Exactly, Annika. Yeah. Wouldn't the red light blast stuff in the first layer? No, because that red light is not energetic enough to break any bonds. So you have to use a particular material in that layer that has much stronger bonds than red light, which is like weak sauce. Okay, but down this lower level, right? No blue light is making it down there because it all got absorbed in the first level. Right, so you're really only hitting the red level with red light only, because the blue and green's been removed in the first two levels. The red light still hits stuff, but I think if you think about these things as just like bullets, you're right, but they're really these particle wave duality things that a bullet really only collides with something if there is a favorable absorption cross section, is sort of the technical way to think about it. But basically all that means is there has to be a response in the material that is matched to that energy. So if the electrons in the atom are held onto so tightly that this weak red light isn't capable of doing anything to it, then the light just passes right through. There is no interaction. It is not just that there's smaller bullets that ricochet off. It's that they don't really interact at all. They pass right through, right? We have windows, the light passes right through. Why? Because there's not a lot of absorbing compounds in the window material, in glass, okay? Are chlorophyll more efficient? Yes. Just tell them the light packets are quanta, done. So you can have, basically anything. Arsenic, antimony can be used, or you can have larger composites of different substances. But you'll see a lot of arsenide as well. Okay, so this is one thing that gets us to higher efficiencies. We can look at this chart again and notice multi-junction cells, right? So crystalline silicon cells, this is where we started the lecture, okay? Early on, most of it was silicon. There was a gallium arsenide one as well, okay? And then there's some thin film stuff, right? But it's these multi-junction cells where you're using a lot of different layers that are getting us up to larger efficiency. So you'll see over here on the right side, as we move on in time, the efficiencies are going up and up and up because we're exploring new multi-stacks of things that get around this 33.3% level, right? Notice the blue things aren't getting up above 33%. You need these multi-stacks to get up, and the world record right now is 47.1%. Lol, yes and no. Sometimes they're physically separated levels, but more often than not, you're right. It's like a composite that has different things throughout it that absorb in different wavelength regions. Yo, what's up, Dr. Young's lab? Texas Space Agency, welcome back. Yeah, it's okay, William. I mean, it's uncomfortable to think about. You only, like, the more you study quantum mechanics and science, eventually you're just like, yeah, okay, it doesn't really make sense with anything I know about the world, but that's the way it is, so I have to be comfortable with it. And it's just about taking some time to get comfortable with that. I'm glad you're living the dream. Is living the dream tagging yourself in a chat message? Because that's what you're doing. That's pretty awesome. Dr. Young's lab at Dr. Young's lab. Okay, so the last thing I wanted to mention here with our solar cells lecture is different materials. We talked about silicon. We maybe talked about doping silicon. I respect it. I'm sad I haven't thought of it myself. But there's a newer class of materials, right? Like notice down here, some of these are leveling off. The newest one is these square guys, okay, squarey, okay? This orange squarey are Perovskites, okay? And they hold a lot of promise, right? There's not really a leveling off here. There's squares up here, pretty big jump, okay? Perovskites at 25%. But they're the earliest, or I should say the most recent, sort of new material that's being explored. And a lot of people think these are very, very promising, myself included, not just for solar cell applications, but other applications as well. And a perovskite is need to talk to a geologist, probably somebody like Rocket Sage, but basically the perovskites, okay, so let's just type, what more can be done? We talked about layering to get beyond 33%. What more can be done is explore new types of materials. Most of what has been done, not all, but most, are silicon-based. Okay, and silicon was the first one. As we talked about, Bell Labs was the first sort of silicon, semiconductor photovoltaic material. And so they had the early movers advantage, like they're the ones that have been studied the most. But perovskites, I'll say it's newer because it's still, I don't know, a decade old or something. Okay. And these, I think, were first discovered in the ground. It's a very common type of mineral. And it's just a general name for certain crystal structures. And now I'm girding out beyond my comfort zone and my knowledge a little bit because I am only, really only know the surface level of perovskites. But basically, we talked about silicon earlier having this nice crystalline structure. You know, like a diamond is carbon in a covalent network. Silicon, a silicon crystal is silicon in this covalent network that you're then doping with phosphorus in our N-type semiconductor. But a perovskite is usually something of the chemical formula, not just like silicon, some n number of silicons, but it's usually two elements and a halide or a oxygen or nitrogen atom in three of them. So this is the ratio 1A to 1B to X, where these A and B are metals. And this X is usually oxygen, but I think it can be a halogen like fluorine or chlorine as well. And these structures are semi-porous, they're strong, they are semiconductor in nature, and they're easily tailorable. Because it's not just silicon, you have a couple different elements that you can change out. Most of the time it's oxygen, but you can do this with calcium and titanium, okay? You can do this with cesium and lead and iodine. Yeah, so usually oxygen, sometimes halogen, where halogens are like chlorines, iodine, etc. And these are the things that are being explored in this graph in the orange squares that are sort of escalating pretty quickly, where a lot of the others are either flat or kind of turning over. And this is sort of the, I think, in my very naive opinion of emerging solar cell technology, what would be the next leap? Now, Sure, these multi-junction ones are great at 44%, 47%. But in order to really meet the demands of, climate change and building, an energy grid that is able to provide clean energy for not just urban locations, but rural, for cheaper countries and richer countries, we need to invest in solar infrastructure, but also solar efficiency. So it is still of utmost concern to me to make sure that my federal government is investing in the research and development of things like perovskites, as well as all these other types of solar energy materials to get us to efficiencies that are 50, 60, 70%. I mean, the more energy we can harness and not lose from heat losses, the more energy we will have. We also have to develop, of course, the infrastructure and the storage capabilities and batteries, but it's going to take all of that to really transition this world off of dirty energy sources like coal, oil, and gasoline. So I think that's where I'm going to end the official lecture. We might watch some videos and talk in more depth about some of these other topics. But yeah, hope you enjoyed learning some of the fundamentals of how solar cells work, and might have a more informed perspective with which to go dig into further videos, books, and educational resources to learn more about it. Enjoy!